Hello and welcome to your stats notes. All right, so this sort of marks a transition in the course. Most of what we've been doing up to this point could sort of be lumped in the category of descriptive statistics, where we have data and we're calculating values that describe or answer questions about that data that we've collected. All right. Inferential statistics is where we collect data and then use that data to make inferences or generalizations or conclusions or what have you about the larger population. All right, so a lot of what we're going to be focused on now is gathering data and then using that data to make estimates about the population at large. All right, so that's kind of the big paradigm shift that we've got for the rest of the course. So with that, let's get a couple definitions down that are going to be important to us. So first, a parameter. All right, a parameter is a number that describes some characteristic of the population. Right, so when we're talking about the population as opposed to a sample, we call it a parameter versus a statistic that we'll put a definition down for in a second. All right, and then with this is the whole idea that I was just talking about. The value of this is usually unknown because we can't examine the entire population. All right, which is why we need a way of estimating it. We need a way of trying to come up with some technique to say, all right, this is our best guess of what the value is, because it's very rare that we're actually able to calculate it directly. Now, a statistic, do you like the irony of defining statistic 7 units into a statistics course? Is a number that describes some characteristic of a sample. All right, so parameter P goes with population, statistic S goes with sample. All right. The value can often be computed directly and then used to estimate the parameter. All right, and again, that's a lot of what we're looking at today. So one thing that I want to point out, all right, S sample statistic, generally the symbols that we're going to be seeing for that is when we're talking about the mean, that's going to be X bar. All right, when we're talking about standard deviation, that's going to be S of X. And when we're talking about proportions, that's going to be P hat. In comparison, when we're talking about a population, all right, we're using these various symbols. So we've got this right here, or mu, for our mean. All right. This right here is a lowercase sigma, all right, and that's what we use for standard deviation. And then when we're talking about a population proportion, it's just P without the hat. All right, so when we're dealing with samples, we use these symbols. When we're dealing with the parameters in the population, we use mu, sigma, and just the regular p there for proportion. Now, a couple other terms that are going to be important, and we have to keep them straight in our heads because they all have similar names, but they all mean something different. So a population distribution describes the values for all individuals in the population. All right, so if you've got a population distribution, that's describing all the values, and it might take the shape of like a curve or a histogram or whatever, but describing all of the values for every single person in the population. All right, I'm going to skip sampling distribution and jump down to distribution for sample data, which describes all the values, or we'll just say describes the values for all individuals in a sample. All right, so we have the population distribution that's describing all the individuals in a population. We've got the distribution of sample data, which describes the values for all individuals in a sample. So what's the sampling distribution? All right, the sampling distribution describes the values for the statistics and in this course, that's mainly going to mean, it's going to mean means, get it? Mean and proportions, right? Those are the two statistics that we're going to be spending most of our time with. All right, so it describes the value for statistics, which in our case is generally going to be the mean and proportion, or means and proportions. In all possible samples of the same size from a population. All right, and this is actually where most of our attention is going to be. So let's talk a little bit about it to try to explain what that actually means. All right, so let's pretend you have a population of 100 people, and you are taking a sample of 5 people and calculating the average height of those 5 people. All right, the sampling distribution is all of the possible averages that could be calculated if you were to combine those people and represent every possible sample of 5 people. So, like, what is the average of person 1, 2, 3, 4, and 5? That would be one data point. Then what's the average of persons 2, 3, 4, 5, and 6? And then what's the average of persons 3, 4, 5, and 7? And the average of 4, 5, 6, 7, 8? And the average of 1, 32, 72, 89, 99, and 100. But literally, if you were to look at every single possible combination that you could make of 5 people from this imaginary population of 100, and you were to calculate an average for every single one of those possible samples, the sampling distribution would be all of those different averages you calculated. All right, so again, maybe one sample had an average of 12, and your second sample had an average of 11.7, and your third sample had an average of, let's say, 13.6. Again, I'm just making things up here. and your fourth sample had an average of 15.2, and you went on and on and on, and basically selected every possible sample, then the sampling distribution is all of the averages. All right, so the sampling distribution is all the averages you calculated. All right, so again, keeping these three straight is going to be important when answering questions in this unit, because otherwise you're going to not really know how to attack them, or you're going to be giving the wrong values or calculating the wrong values. So again, population distribution, all of the individuals, distribution of sample data, all of the values in an individual sample, sampling distribution, all of the statistics that you could calculate from every possible sample. All right. So again, an important thing to kind of keep in mind, an important thing to focus on, because most of what we're dealing with in this unit here is going to be the sampling distribution. All right. So last definition, and then we'll get into kind of what we're doing today. Sampling variability, all right, is generally the variability slash differences, if you don't want to use the same word in the definition, that we expect to see from one random sample to another. So basically, when you're taking samples and trying to estimate a parameter, you're not going to get the same values from your samples every time. All right, there's going to be a variability. Sometimes it might be a little higher, sometimes it might be a little lower, sometimes it might be right in the middle, but there's going to be some variation in your results, because that's just the nature of gathering data and collecting samples. All right, so generally the way the next few units are going to go is we're going to break it down into categorical data, which is mostly going to deal with proportions. And then after we've kind of studied it from the categorical perspective, we're going to switch to the quantitative perspective, which is mostly going to deal with means. All right. So categorical data, again, generally things that fit into categories, things that we can count. So it says here we have to count things. So each sample will give us a proportion. All right. We can count our number of successes. All right. Thinking back to binomial random variables, and we can put that over the number of trials to get a proportion. All right, so the proportion that we're talking about here is generally, the number of successes over the number of trials. But that's the statistic that we're generally going to be calculating when we deal with categorical data. Like, how many times did you succeed in something over how many times did you try to do it in general? All right, so here's the little activity that we would do. All right, so it says normally when you toss a coin, it has about a 50% chance of landing on heads. So if everyone in the class flipped a coin multiple times, we would expect the sample proportion of heads to be centered around 0.5. Again, because of variability, sometimes it would be a little higher, sometimes it would be a little lower, but in general, we would expect it to be 0.5. However, we don't know the expected proportion for tossing a Hershey kiss. So that's a little more interesting. All right, if you keep tossing Hershey kisses, how many times are they going to land on their base so that they're pointing up? And how many times are they going to land on their side? So if you want to follow along at home, you're going to need some Hershey kisses. All right. If you don't have any Hershey kisses, you can just kind of see what I'm going to put down on this sheet. But if you want to follow along at home, you need to just have some Hershey Kisses. You would start by tossing your Hershey Kiss in the air 5 times and counting how many times did it land pointing up. How many times did it land on its base? Right? That's your number of successes. And we're putting it over the number of trials to calculate a proportion. So, for example, you might throw your Hershey Kiss 5 times and it lands, pointing up 2 out of 5 times. So the proportion or the statistic we're calculating from that is 2 divided by 5 or 0.4. So what we would do is we'd have everybody in the class do this. All right, we'd have everybody in the class toss their Hershey Kiss 5 times, and we would record the data. All right, and what I'm going to do is I'm just going to put down some data that we got from a previous year. All right, so in a previous year that I did this, all right, each dot that I make represents one student's toss of the Hershey Kiss. So for example, in this year, I had 1, 2, 3, 4 students that ended up with none face up, right? I had a couple of students that ended up with a proportion of 0.2, which basically corresponds to 1 out of 5. This one's corresponding to 0 out of 5. I had a bunch of students that had a proportion of 0.4, which is basically 2 out of 5. And then I had a bunch of students that had 0.6, which was like 3 out of 5. And I had one student that year that got it 4 out of 5 times. All right. Nobody got it 5 out of 5 times. All right. But that was sort of the general, data that we collected. All right. So our histogram, which really this is a dot plot, basically had 16 sample proportions. All right. Those dots represent the data that was collected, each that had a sample size of 5. So our N up here is 5. All right. So this is sort of like a sampling distribution. All right. We can kind of think of this as our sampling distribution because, again, all right, it's not, the number of ups. It's not an individual sample. It's the individual statistics that we calculated. All right. Each student calculated a statistic, and then we plotted those values of the statistic on our chart here. Now, if we're describing this, all right, we would say that it's probably centered somewhere in the 0.4 range. All right. But we'd also say that it's like, very spread out. All right. And if we were calculating a range on this, the range is from 0.8 to 0, which in statistics words means that our range is just 0.8 here. All right. So if we're subtracting the max value from the min value, that's what we get there. So in general, it's pretty spread out. And the shape is relatively symmetric. It's not totally symmetric, but maybe because of this high, amount of zeros here, you'd say it's a little more left skewed, but it's roughly symmetric, not perfect. But we do have kind of a center here, and then we have it going off to both sides. All right, so that's kind of the first phase of this. All right, we tossed it 5 times, we gathered this data, we see what happens. All right. Next phase of this is to say, okay, this was based off samples of size 5. Right? What happens if we increase the sample size? All right? What happens if instead of tossing a Hershey Kiss 5 times, we toss it 25 times. All right. So if you're at home, you've got your Hershey Kiss, what you'd want to do is toss it 25 times. All right. Keeping track of the number of ups that you received. All right. And maybe you ended up with like 10 or so ups, which would work out to be a proportion of like 0.40. And again, our sample size here is 25. All right. Now, again, I'm going to kind of just basically use data from a previous year, but we're going to sort of collect it into bins now. All right. So instead of doing the exact values, because like here, there were only, what is 1, 2, 3, 6 possible things that you could have gotten. So I could just put them directly on the lines. Here, I'm going to kind of treat these as bins, and anything from 0.4 to less than 0.45, I'm going to put in this bin. Anything from 4.5 to less than 5, I'm going to put in this bin, and so on and so forth. So I'm going to kind of condense it down as sort of like a histogram would be condensed down. All right. And again, looking at sort of previous data that we got in a previous year. All right, here's what we got. So I'm going to put 1 dot in here. I'm going to put 2 dots right next to that. I'm going to put 2 dots here right below 0.4. I'm going to have 1, 2, 7 in this one. So a lot of people ended up right in here. 3, 4, 5, 6, 7. And I'm going to have 2 right next to that. And I'm going to have 1 way out here underneath 0.7. And again, each one of these dots, each dot represents a student's calculated proportion. All right, so again, sampling distribution, because we've calculated a statistic and we're showing all of the different values that that statistic has taken on from all of our different samples. So in pausing the video, I just realized I miscounted. So if you were going back on this page and you were like, wait a second, he only made 15 dots. You're exactly right. I only made 15 dots. So I don't know why I wrote 16 there. The histogram had 15 sample proportions with a sample size of 5. So sorry, if anybody was keeping track of that, my apologies. So we've got our 15 dots here. So we have 15 proportions coming from samples of size 25. All right. Now, if we're describing this, right, the center is still in that 0.4 range. All right. Our shape is still, fairly symmetric. And our spread has decreased. All right. If we were to recalculate the range, and again, these are kind of estimates here, but this is a little over, 2, but we'll just use 0.2. And this is a little less than 0.7, so we'll say, 0.65. But basically, even if we say 0.7 and 0.2, we're seeing that the range has decreased from that first graph where it was 0.8. All right. So one more time, toss the Hershey Kiss 75 more times, or basically 100 times in total. So if you're sitting at home right now, you might be saying to yourself, I'm glad I'm not in school because I don't actually want to toss a Hershey Kiss 100 times. In which case, I would vehemently disagree because you have not lived until you've tossed a Hershey Kiss, at least 100 times. 100's probably even too few. But basically, you toss the Hershey Kiss 100 times, count how many times it landed face up, and maybe you get like 37 or something. So your proportion is just 0.37. All right. And again, our sample size on this one is 100. So again, do it yourself. And I'm just going to put some data that from the previous year like we have on all the other ones. All right. So there was one right here just after the 2.5. And there was 1, 2, 3, 4 right here after the 3. And then there was 1, 2, 3, 4, 5. And then there was 1, 2, 3, 4 right next to that. And then there was 1 down here. So again, let's kind of describe what's happening here. So we have 15 proportions coming from samples of size 100. Right. The center, right, is basically, in this high 3 range. So like, I'm just going to say 3.5, 0.35, 0.35 to 4. All right. Our shape is very symmetric at this point. Now, part of that was just luck that year, but it is very symmetric at this point. And our range is much smaller. All right. Our lowest value is like 2.5, and our highest value is like maybe like 4.5. So we're going from like 4.5 to 2.5. Why do I keep saying 4.5? 0.45 to 0.25, or like 0.2. All right, but each time we increased our sample size, what we should notice is that the center didn't really change. However, the range or the spread of our data became much, much smaller. So what do you notice as the sample size increases? I basically just said that. The center is staying approximately the same, or roughly the same, but the spread is getting smaller. And the shape more symmetric. Right. So why did we do this exercise, or why did you pretend to do this exercise? This exercise, one, is it kind of drives home the idea of what a sampling distribution actually is. All right, it's all these collected statistics from different samples. And two, we're about to look at some formulas. All right, and these are going to help explain why the formulas are what they are, why they include certain values but not others, and kind of how everything fits together here. All right, so if we flip to the next page, it says, hopefully you noticed that as the sample size increased, the data began to look more and more like the normal model. Well, we can use the normal model to help us answer questions about a distribution if certain conditions are met. So what are those conditions? All right. Well, first of all, they're going to look pretty familiar because they're similar to what we discussed in the last unit with binomial distributions. So one is randomization / independence. All right. I'm not saying those are the same thing. I'm saying those are both important. And basically, the results of one trial don't impact the results of another trial. All right, so the randomization piece is just like you should always be sampling, you should always be gathering your data using sort of like random selection so that you're not like letting biases creep into your selection process. And then the independence part is saying, the results of one trial shouldn't impact the results of another trial. Now, we also talked about that when you're sampling in the real world, you're almost always sampling without replacement. Which means technically like probabilities are changing and shifting as one person is removed from the group. But we also saw that that's not a problem as long as the 10% condition is met. All right, so we have this 10% condition, which states that the sample size, which usually we do as n, must be no larger than 10% of the population. All right, and this condition is going to be important to us when we're trying to calculate the standard deviation of a sampling distribution. So this condition directly relates to sort of the standard deviation. All right, and then the other condition that we're concerned with is the success failure condition, which again, we talked about this in the binomial unit, which is basically where we expect at least 10 successes and 10 failures. All right, and this one affects our ability to use the normal model. So if we want to use our normal model to make estimates, that has to be in place. So if the conditions are met, the sampling distribution is modeled by a normal model, right, with these following conditions in place. All right, the mean of that normal model is the mean of the sampling distribution. All right, so this is saying the mean of p hat. All right, what is the mean of p hat? The mean of p hat would be, consider this your sampling distribution. All right, these are all the proportions we calculated. If we average together all of these proportions, that's the mean of the sampling distribution. All right. So notice this doesn't actually involve sample size, which is kind of what we saw. All right, it didn't matter what our sample size was. If our sample size was 5, the mean of all of these values was still roughly 0.4. If our sample size was 25, the mean of all of these values was still about 0.4. If our sample size was 100, the mean of these values was still about 0.4. So this is basically saying that the mean of all the sample values is equal to the true population parameter. All right. So the mean of all the sample proportions is equal to the population parameter. So going back to our Hershey Kiss experiment there, that's telling us that the odds of a Hershey Kiss landing, pointing up or base down is basically 0.4, because the average of these values should be the true population parameter. The average of these values should be the true population parameter. Now, the standard deviation piece, that does involve sample size, which is, again, what we saw with the Hershey Kisses. As our sample size increased, the standard deviation went down, right? As our sample size increases and we divide by a larger number, our sample size is going to go down, all right? And again, this is the spread of the sampling distribution, or our normal approximation of the sampling distribution. But it's how spread out the sample proportions are, all right? So let's put another thing. So it's basically how spread out the sample proportions are. All right, but that's what that's measuring. Now, you may not recognize it, but each of these formulas actually ties back to the binomial distribution, right? On the first page there, I said that we're basically doing the number of successes divided by trials. So when we're calculating a proportion, it's basically x, which is a binomial variable, divided by n. Well, we know that the mean of a binomial variable is n times p, and when we divide n times p by n, we're just left with p. We know that the square root of a binomial variable, the standard deviation of a binomial variable is the square root of n times p times q. And if we divide that by n, all right, to get the n inside of the square root, we could rewrite this as the square root of n times p times q over n squared. All right, one of those n's cancels out, and we're left with this formula over here. All right, so these formulas are extensions of the binomial formulas we learned last time. All right, this one just breaks down to p, and this one breaks down to, where do I want to write this so that I have room? I'll just write it over here, pq over n. All right, so that's where both of these formulas are coming from. All right. Now, how are we going to use them? What's their role going to be? What type of questions are we going to be looking at? All right, so we have a USA Today poll that asked a random sample of US adults what they do with the milk in the bowl after they have eaten cereal. So, a super important question. Of the respondents, 67% said they drink the milk. All right, I'm part of that 67%. I drink the milk. Suppose that 70% of US adults actually drink the cereal milk. So this 67% represents a statistic because it's calculated from their sample. This 70% represents the population parameter. Now, where did this come from? Well, we're just giving it to you in the problem, but we're saying that 70% is the population parameter for the percent of adults who drink cereal milk. All right, so this first question says, find the mean and standard deviation of the proportion of each sample that say they drink milk. All right, so this is basically saying the mean and the standard deviation of the sampling distribution. All right. And standard deviation of the sampling distribution. Now, there's not just one sampling distribution. The sampling distribution changes based on your sample size. All right, so this is the mean and the standard deviation of the sampling distribution for n equals 1012. All right, because remember the sampling distribution is every possible sample that you can have from a population of a specific size. So we're talking about the mean and the standard deviation of the sampling distribution when n equals 1012. Now, what we saw with the Hershey Kisses is it didn't matter what your n was. When you averaged all of those individual statistics together, it generally worked out to be the same thing. So again, the way we write this is the mean of all of those proportions that we could calculate is equal to the true value, and the true value is given to us in the problem as 70%. All right. The standard deviation of those sampling distributions, all right, so the standard deviation of p hat is going to be this pq over n, all right, and this does involve our sample size. So we've got 0.7 times 0.3. All right, and I know it's 0.7 because our formula is PQ, not P hat Q hat. So we're using the population parameter value, P and Q, so 0.7, 0.3, over the sample size, which in this case was 1,012. All right, so let's just put that in the calculator. 0.7 times 0.3 divided by 1,012. Take the square root of that. We've got 0.0144. 0.0144. So just taking it back to the Hershey Kisses for a second, right? You'd expect, a curve that was centered around 0.7 with a standard deviation of 0.014%. All right, so you're going to be pretty tightly condensed around that 0.7 because our sample size was so large. As the sample gets larger, the spread of your sampling distribution gets smaller and smaller and smaller. So explain why you can use the formula for standard deviation in this setting, right? So the reason we can use the standard deviation formula, even though we are sampling without replacement, so even though we're sampling without replacement, it's fine because 1,012 is less than 10% of the population of US adults. Okay. So again, that's this condition up here, which relates to whether or not you can use this, standard deviation formula when you're sampling without replacement. All right. Find the probability of obtaining a sample of 1,012 adults in which 67% or fewer say they drink cereal milk. All right. So first we have to establish that we can use the normal model. All right. So to establish that we can use the normal model, we need to have 10 successes and 10 failures, which we can find by doing n times p and n times q. Now, in this case, there's going to be plenty because we're basically doing, 1,062 times 0.7, and we're doing 1,062 times 0.3. And in both cases, that's going to be well above 10. So, we are more than okay in this situation to use the normal model. So we've got 743.4, and we've got 318.6. And again, this is what we saw with the Hershey Kisses, but once you had enough successes and failures, the sampling distribution looks very normal, and you can start to use it to approximate different percentages and proportions. If you try to use it when you don't have enough success and failures, you're going to get very poor results because the distribution hasn't really taken on that normal shape yet. All right, so all of these things keep tying back to what we did here. All right, so once we've established that we're okay and we can use this, then it just becomes an NCDF from -9999 to 0.67, because it says 67% or fewer, when the mean is 0.7. All right, again, the mean of our sampling distribution we found to be 0.7, and the standard deviation of our sampling distribution to be 0.0144. All right, and if we put that into the calculator, second distribution, normal CDF, -999 to 0.67, when the mean is 0.7 and the standard deviation is 0.0144, we get something like 0.0186. 0.0186, or you could think of that as 1.86%. All right, so that's how we can use this as part of, a larger problem. All right, continuing on. All right, so we'll go through these ones a little quicker because it's pretty much the same thing again and again and again. So Harley-Davidson motorcycles make up 14% of all motorcycles in the United States. So again, that would be our parameter. You plan an SRS of 500 motorcycles. All right, so this would be our N value. What is the mean and standard deviation of P hat, the proportion of each sample that owns Harleys? So that's asking, what's the mean of your sampling distribution if you were to keep calculating these over and over and over again, right? And we know that the mean of the sampling distribution always works out to be the parameter P. So the problem gives us to that, it's just 0.4. Now the standard deviation of our sampling distribution, all right, or the standard deviation of all of those different proportions we could calculate, that's our PQ over N. All right, and here we have a P of 0.14, which means we have a Q of 0.86, and the problem told us that the sample size is 500. So 0.14 times 0.86 divided by 500 is a really small number, but then when we take the square root of that, it works out to be 0.0155. So 0.01, 0.0155. All right, so this tells us that when we're collecting data, 500 people at a time, all right, it's going to average out to be about 14%, but the standard deviation on that is 0.0155. So sometimes you're going to get a sample that's a little lower than 14%. Sometimes you're going to get a little sample that's higher than 14%. So this one says, how likely is your sample to contain 20% or more that own Harleys? So if you take a sample of 500, what are the odds that you get 20% or more with Harleys? So given that we know we expect to get 14, this is basically saying, what are the odds of getting 0.2 or higher when the expected value that you're supposed to get is 0.14, but the standard deviation is 0.0155. All right. And again, that's just our distribution menu, normal CDF, 0.2, 9999, 0.14, 0.0155, and we get 5.42 times 10 to the negative fifth. So let's write that like this, 5.422 times 10 to the negative fifth, or 0.1234 5422. All right, so it's a really tiny value, which makes sense because 14 is the average value. The standard deviation is only 1%. So you're talking like 1.5%. So you're talking almost like 3.5 standard deviations above the mean. So yeah, that should be really tiny. All right. C says, how likely is your sample to contain at least 15%? All right, so that's saying 0.15 to 9999 when the mean is 0.14 and the standard deviation is 0.0155. This one should be a lot higher because now we're relatively close to the mean there. All right, it's still going to be under 50%, but it should be quite a bit higher than the first one that we did. So 0.15999, everything else stays the same, and 0.2594. 2594. Okay. So again, using these formulas, finding a mean, standard deviation, and then using those means and standard deviations inside of sort of an NCDF calculation. All right, BMI. The Center for Disease Control and Prevention reports that 22% of 18-year-old women in the US have a body mass index of 25 or more that can sometimes be associated with increased health risk. As part of a routine health check at a large college, the physical education department requires students to come in and be measured and weighed. This year, the department decided to try out a self-reporting system, and it asked 200 randomly selected females to report their heights and weights from which the BMI would be calculated. Only 31 of those students had a BMI greater than 25. Is this proportion of high BMI students unusually small? Describe what you would expect the distribution to look like. All right, so this 22% would be our parameter. And then the 31 out of 200 which works out to be 0.155, would be our sample statistic. So we want to find out how unusual is this? What were the odds of getting a sample where it was 15% with a high BMI, given that the US population has 22% of people with a higher BMI? All right. So if we want to make this estimate, we want to be able to use, these formulas. We want to be able to use the normal distribution. So we need to check our conditions. All right. Is our sample under 10% of the population? All right. That's the first question we're asking. And the answer would be yes. All right. 200 is well below, the population, the 10% of the population of 18-year-old females in the United States. Do we have 10 successes and 10 failures? All right. We do. All right, because, all right, we have a sample size of 200. We have an expected value here, or an expected parameter of 0.22. All right. And then we also have the flip side of that would be times 0.78. So 200 times 0.22 gives us 44. And these are always going to add up to 200. So this one must be 156. So we do have 10 successes and 10 failures. So we're good there. All right. It tells us that they were selected randomly. All right, so that is also one of our conditions. And we also know that each person is independent of one another. Like, there's no reason to expect that if one person has a high or a low BMI, the person next to them is going to have a high or a low BMI. All right, so we're good there. So if we want to find the mean of p hat, again, that's just equal to our parameter, 0.22. If we want to find the standard deviation of p hat, we're going to use PQ over N, which in our case is 0.22 times 0.78 over our sample size of 200. So 0.22 times 0.78 divided by 200. Take the square root of that. 0.0293. And then to check to see if P is unusual, right, we're basically saying, what are the odds of getting this value or lower? So since we're going lower, what are the odds of getting this value or lower when the mean value that you're expecting is 0.22, but the standard deviation is, 0.0293. All right, so even though this is what you're expecting, you do recognize there's some variation, but that's, saying the amount of variation you should expect given that your sample size was 200. So we go here, normal CDF, negative 999, 0.155, 0.22, 0.0293. And it's telling us that it's 1033. So there was a 1% chance of getting this value if this parameter is true. All right, so if this parameter is true, there was a 1% chance of getting a sample that only had 15%, which might suggest that self-reporting is not as accurate as actually, doing the measurements in that way. All right, so, getting a sample value of 0.155 when n equals 200 is fairly unlikely. Okay. So let's take a look at the back here. Of all the cars on I-90 between exits 9 and 10, 80% exceeded the speed limit. What proportion of speeders might we expect to see in the next 50 cars? All right, so the first thing we want to check is our conditions. So there's a lot of cars on I-90, so, 50 cars is under 10% of the population on I-90, so we're good there. And then as far as the 10 success, 10 failure condition, all right, we've got a sample of 50, so 0.8 times 50 is 40, and 0.2 times 50 is 10, so both of those check out. So we're good there. So our sampling model is we can use a normal model. And that right there is because of the 10 success, 10 failure condition. All right. And we can use, even though we're sampling without replacement here, all right, this allows us to use the square root of PQ over N. All right. So just a reminder that that's what those conditions kind of correspond to. So the mean of our sampling distribution is just going to be that 80%. Okay, that's our population value. So the mean of our sampling distribution will always work out to that population parameter. And the standard deviation of that is our PQ over N, which in this case is 0.8 times 0.2 over 50. All right, so 0.8 times 0.2 divided by 50. Whoops, 0.8 times 0.2 divided by 50. Take the square root of that. 0.0566. 0.0566. And because we know that it's a normal model, all right, because we know that it's a normal model, 95% will be plus or minus 2 standard deviations from the mean. So based on that, we can say we expect the sample proportion to be roughly, all right, I'm just gonna kind of estimate here, but if we call this about, 5.5%, so I'm gonna go like 11 up and 11 down. So 11 down would be between 0.69 and 11 up would be 0.91. All right. So again, just different ways that we can kind of use these formulas to answer sort of different questions. All right. Now, one last definition, and then we'll end this, unusually long notes video. So sorry about that. An unbiased estimator. All right. That's what we've been using. But what does it mean to be an unbiased estimator? All right. A statistic is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. All right, so something's unbiased if when you average all these together, it works out to be the true value. All right, something is biased when if you average all those things together, it works out not to be the true value. All right, so what's an example of a biased estimator? All right, well, something like the range is a biased estimator. All right, and here's why. All right, imagine if we were trying to calculate the range of the human population. Well, at last checked, the tallest person was 8 feet 3 inches, and the shortest person was 1 foot 9 inches, which means the population range, or the population parameter, is 6 feet 6 inches. Right. Now, if you start sampling and calculating ranges, so let's say I take 100 people and calculate their heights and calculate the range, and I take another 100 people and calculate their heights and find the range, and I calculate another 100 people, all right? I'm not going to get 6 feet 6 inches, all right? Because to get 6 feet 6 inches, I'd have to have both the tallest and the shortest person in the world in my sample. I'm probably going to get much smaller ranges. I'm probably going to get ranges like in the 1 to 2 feet range. So no matter how many samples I get, it's never going to average to 6 feet 6 inches, right? Range is a biased estimator. It's not going to give us the right answer on average, where proportions on average are giving us the correct values. All right. This is the reason that we do the n-1 for standard deviation. All right. When you're taking a sample standard deviation, if you divide by n, it's biased. On average, it underestimates the spread. Right? When you divide by n-1, it's unbiased. Right? In any given sample, it might not give you the right value, but on average, it's going to give you the correct value. All right, so all of this stuff that we did throughout the notes kind of relies on it being an unbiased estimator. So we're always trying to use unbiased estimators, because if you have a biased estimator, like range is a biased estimator, we can't use a lot of this stuff that we just talked about, because on average, it's not going to give you the correct value. On average, it's going to give you an incorrect value, which means we can't use all this stuff that we just talked about. All right, so proportions are an unbiased estimator. Means are an unbiased estimator. Things like range and standard deviation. Well, range is a biased estimator. Standard deviation, it depends. If you divided by n, it would be biased, which is why we divide by n-1. Right? That's the whole reason we do it with an n-1 there. All right. So I hope this was useful. If you have any questions, obviously reach out and we'll go from there. All right. Have a great day. Bye.